Hello and welcome. My name is Donnie Walsh, and my parents only taught me 25 letters of the English alphabet. I don't know why. In this video, or videos, depending on how long it takes, I'm going to walk through the code of Bad Guy in its current state, version -4. The code has been moved around from paradigm to paradigm as I design iteratively, so I will point out areas that are behind the times, so to speak. I won't be doing any modification during this video as my recording computer is only rigged to view the code thus far. All the code that we're looking at, as well as the MongoDB raw data, is available in the Bad Guy GitHub repository. Finally, this video I'm working off has the latest code, which as of right now is commits from February 20th, 2018. Alright, here we go. Bad Guy is built on the MEAN stack. MEAN is an acronym and it stands for MongoDB, Express, Angular, and Node.js. Express and Node.js are mostly just along for the ride and have not been modified beyond environmental tweaks and configuration. MongoDB is currently being used for the singular purpose of importing human-readable flavor and gameplay text, which leaves Angular, which is where the most everything else that isn't related to grabbing and displaying human-readable text happens. If this design seems strange, it's because I intentionally organized things so I would be coding primarily in Angular 4. My only professional development experience so far was very heavy in Angular 4, so Bad Guy was originally conceived as a vehicle to demonstrate things that I've learned professionally as a portfolio piece. Nowadays, I'm prepared to let Bad Guy evolve naturally, which may involve rethinking, shoehorning everything into Angular 4. Anyway, that's the stack, so let's talk next about the architecture of Bad Guy. Bad Guy is based loosely on an MVC pattern with some deviations. MVC stands for Model View Controller, and I won't define the pattern here since there are plenty of resources that do a better job than I could. Instead, let's look at Bad Guy's unique interpretation of MVC by understanding the code that supports schemes. Schemes are a good place to start since they exist on a level above all other data objects. Each scheme you see in the Scheme panel is represented by a Scheme object. If you have access to a Scheme object, you can determine its attributes and modify them. Because schemes impact all other game mechanics, they are made available to the rest of the game via the base class. More on that later. Now, on the screen in front of you, we're going to take a look at the two biggest pieces of this stack, which are Angular and Mongo. Specifically, we're going to focus in on schemes. So on the right-hand side, we have MongoDB, the schemes database table. For each scheme, there will be the ref variable, which is just an integer, increasing from 0 to the ID number of the scheme, as well as the name of the scheme. So when in the scheme panel you're actually looking at the flyout, it's going to display a lot of the information you'll find in MongoDB. It's going to show you the name, it's going to show you the description, and the flavor. All of this is fed into Angular, into a data object, by MongoDB. So each scheme will eventually have a 20-piece array for the description as well as the flavor, and then depending on what level, that's what it's going to show you in the flyout. Now, this is what's coming from MongoDB. However, to build scheme objects properly, we actually need to amass data from MongoDB as well as other sources. So like I said, MongoDB provides the human readable information, but we also need a collection of number arrays that describe advancement thresholds. These are going to be the XP targets, cache costs, and layer rec arrays, and they are provided by the base class. Over on the Angular side, we're looking at the scheme model, which defines the scheme object. It comes with some familiar fields, such as the ref, which is fed directly from MongoDB, just like description and flavor, the arrays of strings that come from Mongo, and the tree, which is a single string that tells you what tree the scheme comes from. During the course of using a scheme, when we try to determine if the scheme is advanced to the next tier, we need to consult the XP target array. If the scheme is a high enough level, it will also need to look at the layer requirement array or the cache costs array. These come from the base class. There is a suite of arrays. For example, XP has two different arrays. The standard XP array, which nearly every scheme gets, and then the beginner layer XP array, named for the first scheme to deviate from the standard pattern. These arrays are used as building blocks to assign into an array of arrays that is consulted during the construction of a scheme object. Mastermind is then constructed with the standard XP array right here, and as we go down the list, starter layer, king's castle, and maintenance all receive the beginner layer XP array. Now, a similar technology is used for the cache arrays as well as the layer requirement arrays that are built and pieced together with deviations if the scheme has a different requirement. As a quick aside, these building pieces being on the base class is a remnant of an older architecture. They actually better belong in a service, although I haven't really found the best service to move them to, so they're existing on the base class just for the time being for legacy reasons. Finally, when we're constructing our scheme object, we need to know the unique player stats for each scheme. Numbers like level, XP, and cache track the player's scheme progress and will be extracted from the player's save string or generated at default levels if a new game is started. This is a lot of effort to build a relatively simple model, but the benefit is plain to see. Because all this is being done first thing, when a game session starts, the in-game logic is able to interact with scheme objects quickly and efficiently. If I want to balance the speed of the game by modifying the scheme XP requirements, I can simply jump to the base class and change the values of one variable that has been assigned to many schemes. If I decide to change the icon for an individual scheme, changing one line in the scheme class allows me to cascade the change across the entire application. These two examples are real, and in both cases I was able to leverage this structure to make fast changes. Now that we have a scheme model constructed and made available through the base class, let's shift gears towards the C in MVC, the controller. Bad Guy is delivered via a suite of services that handle the logic and inner workings of various gameplay areas. For schemes, the scheme object exists to track and hold data about itself. We need a scheme service to digest that data and make decisions on what to do when gameplay events occur. When the player selects a scheme, the scheme service remembers which scheme was selected and handles numerous requests for other services about what to do. For example, when a scheme earns XP, in most cases all we need to do is increase the scheme object's XP value by a certain number and call it a day. At this point, however, the scheme service will check to see if the new XP number is greater than or equal to the current level's threshold. If this check is true, the scheme service handles the act of resetting the XP value to 0 and incrementing the level by 1. Additionally, state-based player variables are modified so that the display is properly updated to indicate that a scheme has been learned and that nothing is being schemed until the player makes a new selection. Some services are tied to a gameplay area, like how schemes have a dedicated object or model and service. Other services, like the system service, focus on non-gameplay functionality. The system service is large, despite holding one string and two functions, but it serves a critical purpose by handling and saving and loading of player data. Bad Guy's save load functionality is very fresh and only in its first iteration, but what it's doing is very straightforward and is not likely to change drastically. Player's game data is stored in a string that is automatically written to a cookie every minute when the game loads. It will look through this string and parse the data to build back to the stored game state from scratch. If there is no stored data, the game will proceed in the same fashion, instead parsing the fresh game string that is included at the top of the system service. This handy parallel design allows for both loading and initiating a new game to use the same function. So saving the game to a string like this is very insecure, and if you wanted to give yourself a boost by modifying the string, all you would have to do is read through the system services comments to figure out which position, say, player cache is stored at. If you change the number in that position to 5 million, refresh the game and you'd be sitting on 5 million cash as soon as the game loads. I'm not worried about this weakness right now, and I'm not even convinced that parsing a string will remain the viable approach to saving and loading game data as Bad Guy grows. Every time a new feature is added, I have to consider what values need to be saved for the player, and various gameplay mechanics I've considered look to introduce a large memory load for saving the game state. So with many things coded so far, I have to keep it around, plan to keep it around until it breaks, and I'll find a solution then. So inside the system service, at the very top, I have broken out the fresh game string to help myself see what values reside where. So while what's happening inside this get fresh game function, this getter here, is just a string that's being concatenated together by a series of plus symbols, but there's also comments mid-string that explain what's going on. So right here on line 29, it would be the exact same thing if I were to write this, but I'm writing it in the way that I have just so that it makes more sense. I can look at this block and see there appear to be 12 different schemes that it's counting. Because I know that there are only 12 schemes coded into the game so far, that makes sense, and it's easy for me to see. If it were one very long string, that becomes a lot harder to see. The order is somewhat meaningless. This string is sort of grown as I create new features and implement them into the save load functionality. So there's no rhyme or reason to the order. The only way that I do take advantage of the order is I know that the first character is going to be a Boolean, so it does not get a Z to separate it. There's no real reason to do that. I just sort of put it together that way, so that's the way that that starts off. Inside of the system service, there is the save reader function. And what this function does is it leverages the fact that I will only ever be reading the save string from one particular position. And because of that, it's going to include its own count variable, which is used for checking to see if it's been inside the loop for more than 50 loops. Sometimes, because the save string is just haphazardly built and Z's are implemented, using them as the breakpoint means if the save string wasn't constructed correctly, or if I'm working off of, say, an older version of the save string that's shorter, I would run into issues where the save reader would not terminate. So this was put in as sort of a release valve to break us out of this loop in case we do run into issues with the save string. Furthermore, this save reader is leveraging a globally available, global to this service available variable called marker. So marker is up here and it's not defined. Inside of the load function, we define marker as 0 right from the get-go. Now we do this after checking the first position of the string for earning scheme points. And that's because the marker is incremented first, at the very first step of the save reader. So we know that it's at 0 after we read base earning scheme points, that first position Boolean character, and then we move into the save reader function, which increments it up to 1. So every time you see save reader, you know that it's sort of where we're at right now, but it will step forward by 1 once it reaches being called. The load function is very, very large, and what it's doing is it's going to parse through a save string, either the fresh game save string or one that's held in the cookie by the user, and it's going to read and set base values, starting with earning scheme points, moving to notoriety, and then into schemes. And it can do this, it's doing that with either the fresh game string or the string from the user's cookie, and it will create the game state from just that data. So the interesting thing about this save string is it contains all of the data that you need to recreate the save state. I'm sort of just saying the same thing back and forth and from different angles, but it's important. This is the backbone of Bad Guy. Every game needs to be created from a save string, and I think I've said pretty much everything I need to say about this without just repeating myself over and over again. So I will go ahead and end this video now. We're at about the 15-minute mark, and we'll explore more about the V in the MVC pattern as well as some more of the design principles and architecture at work in Bad Guy. Thanks a lot for joining me.